So here we're going to be talking about significant figures. In order to do that, just give us a little bit of background on different types of numbers. So when we're doing science, we're doing uh, measurements, we have different types of numbers that we encounter. And there are two broad categories of numbers. These are exact numbers, which we obtain by counting. So if you were to count the number of people in this Zoom session, we would know exactly there are 23 people. So that's an exact number. So there's no discrepancy in the value of that number. We know it's exactly 23. Just like if you were to count the number of eggs in an egg carton, you know there's exactly 12 eggs in an egg carton. Again, there's no what we call uncertainty in that number. Or if we count the number of electrons in an atom, for example, we know that there's exactly 8 electrons. So if you can obtain the number by counting, it's what we refer to as an exact number. There's no uncertainty in its value. Along with numbers you can count, there are also what we refer to as conversion factors within the same system of measurement. And again, system of measurement, we're talking about the metric system and the English system. So if it's in a conversion factor that only remains in the metric system, it's an exact number. So for example, if we say there's 100 centimeters in 1 meter, this would be exact because centimeter and meter are both metric. So since they're both metric, it's an exact number. So there are exactly 100 centimeters in 1 meter. Likewise, with English conversion factors or standard, which is what we use mainly in the US, we know that there's 16 ounces in 1 pound. So both ounce and pound are the English standard system. So this would be an exact conversion factor. And so again, exact means that we know exactly there are 16 ounces in 1 pound. There's no discrepancy in that value. Likewise, if we have 12 inches equals 1 foot, again, inch and foot are both in the same system, the English system of measurement, so it's an exact conversion. So whenever you see that both units in a conversion factor are in the same system of measurement, it's an exact quantity. So if we look at another metric one, you know, if we, for example, we say 1 liter equals 1,000 milliliters, this is an exact quantity because liter and milliliter are both metric. Now, the only conversion factor that's a crossover between metric and English that is exact is the inch to centimeter. So this is the only one when you have an English and a metric unit in the conversion factor that you have that is exact. So there's exactly 2.54 centimeters in 1 inch. That's exact. There's no uncertainty with that. And again, conversion factors are used when we're converting from one unit to another, and that's discussed a little bit later on in another lecture. So that's exact numbers. Again, you can obtain it by counting or a conversion factor within the same system of measurement. Now, where there's a big change is when we go to measured numbers. So with measured numbers, you have to use some type of device or tool to measure the value. So for example, if we're measuring length, maybe we use a tape measure. A tape measure measures in inches, feet, or centimeters, etc. So you have to use a measuring tape to measure length. Likewise, if you wanted to measure weight, you would have to use a scale to measure the weight. So that's a measured number. So it's used, you have to use some type of tool to get the quantity. That's different than saying how many eggs in a carton. Well, with how many eggs in the carton, you can just count the individual eggs. So like 50.1 miles, that's a measured number because miles, the way to obtain it is to use some type of measuring device. Now, this doesn't mean that you physically have to go and measure it. It just means that something was used to measure that distance. So for example, if I just put 27 feet, now feet is something you measure. Even though it's just 27, even though it's 27, it doesn't mean it's exact. It just means that this measurement is only known to the ones place, because since we're measuring, or since we're using the unit foot or feet, this is a measured number. And so besides a number obtained through measurements, any metric to English conversion factors are measured numbers. So what do we mean by that? For example, 1 foot equals 0.348 meters. So you see you have foot on one side, which is English, meter on the other side. This is a measured quantity. So these are conversion factors that are only known to a limited number of decimal places. And so when you use a tool or device to obtain a quantity, there's some type of uncertainty associated with it. So the more precise the tool is, the smaller the uncertainty is associated with it. So for example, if you were to take for example, a yardstick and measure your height, and then take a ruler, which is a little bit more precise measurement, and measure the height of yourself, you would get slightly different answers because of the different tool used in the measurement. So when we're doing measurements or we're dealing with measured numbers, we have certain digits that are significant. That means they're important. So for example, when we look at this 50.1 miles, what this means is that we know this value to the 10th place. After the 10th place, we don't know what comes after. There's some uncertainty associated with it. So it's just 50.1, but we don't know if it's 50.13, 50.14, etc. And it really doesn't matter because only the significant digits are shown. So we only know the miles to the 10th place. Likewise, if we were to look at 3.84 centimeters, again, we know this. Maybe we use a slightly more precise measuring device. We know it down to the hundredths place. But after the hundredths place, again, it's uncertain. So we don't know what comes after it. Whereas for exact numbers, we know it's exactly that quantity. With measured numbers, we only know the quantity down to the number of digits that are significant. And so now we're going to talk about the different types of significant figures that we have. So now when we're dealing with numbers, we have to determine which digits are significant. And just to start off with, when we're dealing with measurements, and we'll talk more about this in the future, but in measurements, it's the number of certain digits plus one uncertain digit. That's how you get the number of significant figures in the measurement. Now, the uncertain digit depends on your measuring device. The more precise the measuring device is, the smaller the uncertain digit is. What I mean by smaller means it may be the tenths, the thousandths place, for example. Now, if we're given a number and we're asked to identify the number of significant figures there's a few rules we have to remember. So the first rule is any non-zero number is significant. So for example, if we had the number 745, since all of those numbers are non-zero, this means it's this means that all of them are significant. They're all important numbers for this measurement, say 745 centimeters. So that's the first rule. Anytime you see a non-zero number in a number, it is significant. The second rule is scientific notation. So scientific notation is a way of writing really small or really large numbers. So for example, if we have 6.507 times 10 to the 8th, say this is pounds. Any number written in scientific notation, all of the digits shown are significant. That includes non-zero and zero digits. So this would have 4 significant figures. So again, anything shown in scientific notation is all significant. They're all important digits for that number. In the third rule, we're dealing with exact numbers. And so the way to remember exact numbers, if you look at the unit, if the unit is something that you can count, it's most likely an exact number. Or if it's a conversion factor within the same system of measurement, it's an exact number. And with exact numbers, we have unlimited significant figures, because we know that 12 eggs in a dozen is 12.00000 all the way to infinity, because we know it's exactly 12. So with exact numbers, we say there's unlimited or infinite number of significant figures. And again, those are the way you pick those up is you look at the units. Is it something I can count? For example, apples, books, atoms, electrons. Those are all things you can count. Those are exact numbers. And also the conversion factors within the same system of measurement, say 100 centimeters in a meter, 1,000 meters in a kilometer, etc. So those are fairly straightforward rules. Where the discrepancy comes is when we're dealing with zeros. And so zeros have its own set of rules that we have to deal with. And there are 3 different types of zeros in a number. The first one are what we call leading zeros. So with leading zeros, these are the zeros to the left of the first non-zero digit. So as you see here, we have 0.0035. Since these zeros are to the left of the first non-zero digit, all of these zeros are not significant. We call them insignificant. And so those do not get counted as significant figures. So if you wanted to write this number in scientific notation, let me write it here, 0.0035. So if we wanted to write it in scientific notation, again, remember with scientific notation, you have to move the decimal place either to the left or to the right to get a number between 10. Now remember, if you move the decimal place to the left, it's a positive exponent. If you move the decimal place to the right, it becomes a negative exponent. So again, what we do is we take the decimal place, we move it 1, 2, 3, 4. We move it 4 places to the right. So therefore, since it's moved to the right, it's going to be negative. So this would be 3.5 times 10 to the negative 4. And you see, remember, anything in scientific notation is significant. So this also confirms that there are 2 significant figures in the number, because leading zeros are never put in scientific notation. That's why they're insignificant. So that's one type of zero. The next type of zeros are captive zeros, and these are zeros between 2 non-zero numbers. So if you see zeros between 2 non-zero numbers, these are significant. They're important in the measurement or the number. The last one is trailing zeros. With trailing zeros, these are zeros at the end of a number. And so with trailing zeros, it depends if there's a decimal point or not at the end of the number. So for example, if we look at the number 100, we have 2 trailing zeros, but notice there's no decimal point at the end. So this would just have one significant figure because these zeros are not significant. However, if we do put a decimal point, say 100.0, now that we put this decimal point here, these zeros become significant. So therefore, we would have 4 significant figures. So trailing zeros are only significant when there's a decimal place or decimal point put. So again, how would you write these in scientific notation? So one has one significant figure, one has 4. So let me go over here and we'll show you. So we have 100 and we have 100.0. So for the first one, imagine that there's a decimal point right here. And so we move it 1, 2. So since we move it 2 places to the left, it's going to be a positive exponent. So we would write 1 times 10 to the second. Notice in the scientific notation, we only have one significant figure, which is in agreement with our 100 that also has one significant figure. Now in the second number with trailing zeros, if we move the decimal point, we have to move it to the left 2 decimal places. So again, we're going to have an exponent of 2. But since we have that decimal point, it's going to be 1.000 times 10 to the 2. So you see the difference when there is a decimal point and when there isn't. And both, when you write it in scientific notation or you keep it in regular number format, should have the same number of significant figures. It won't change. So again, to recap with zeros, we have leading zeros. So they're to the left of the first non-zero number. These are not significant because they're not included in the number when you write it in scientific notation. We have captive zeros, which are between 2 non-zero numbers. These are significant. And we have trailing zeros, which are significant only when there's a decimal point present. So trailing zeros are to the right of the last non-zero number. Now, one question comes to mind when dealing with significant figures is, what happens if we have a number like 0.00230? So when you have a number like this, again, the leading zeros are not significant. So we can cross those out. But then you see the 0 at the end. This is significant because we have a decimal point in the number. So if we were to write this in scientific notation, remove the decimal point. Let me change the color. We go 1, 2, 3, 4. Since we move 4 places to the right, it's negative. So this would be 2.30 times 10 to the negative 4. So the 0 at the end of a very small number is significant. So you need to include it when counting significant figures. So now let's look at some examples. I have some numbers here. We want to identify the number of significant figures in each one of these numbers. So first we have 0.00305. So this number has both leading zeros and it has a captive zero. And remember, leading zeros are not significant. So this would only have 3 significant figures. Because again, leading zeros are not significant, captive zeros are significant. So this 0 is between 2 non-zero numbers. Likewise, if we go to 1.008, again, these three zeros between 1 and 8 are captive zeros because they're between two non-zero numbers. And remember, all non-zero numbers are significant, and captive zeros are also significant. So this would be 5 significant figures. Next, we have 12,000 with a decimal point. So this 12,000, these three zeros are what we call trailing zeros. And these are significant because you see here, we have a decimal point. So that's very important in this number. So this means we have, 5 significant figures. Over here we have 505,000. This is a combination of captive and trailing zeros. So again, the zero between the two fives is what we call captive. The three zeros to the right of the last non-zero number is captive. So these are insignificant because there's no decimal point. So this would be 3 significant figures. Next, we have a number in scientific notation. Remember, all digits in scientific notation are significant. So this would be 4 significant figures. And then lastly, 808, we have a captive zero. So this would also, this zero would be also significant. So it would have 3 significant figures. Now what I'm going to do is, just to show you, to confirm these are the correct sig figs, is the ones that are very large and small, I'm going to write them in scientific notation. So if we look at the first number, we have to move the decimal place to the right to get a number between 1 and 10. So we move it 3 places to the right. So since we move it to the right, it's negative. So this would be 3.05 times 10 to the negative 3. So you always want to move the decimal place either to the left or to the right to get a number between 1 and 10. Now if we go to 505,000, if we look, we pretend there's a decimal point here, we count, we go 1, 2, 3, 4, and 5. So we moved it 5 places to the left to get a number between 1 and 10. So since we move it to the left, it would be a positive exponent. So notice when we write in the scientific notation, we just write 5.05 because those are the only significant figures in that number. Now we go to 12,000. Again, we move the decimal point 1, 2, 3, 4. So 4 places to the left. Again, when you move to the left, it is positive. And since there's a decimal point there, we have to include all those zeros as well. Now you may ask, well, how would it look if it didn't have the decimal point? So let's say we just had 12,000. So again, you would still move the decimal point 4 places, or excuse me, 5 places to the left. But when you wrote it in scientific notation, it would just be 1.2 times 10 to the 5th. So see the difference when there is a decimal point and when there is not a decimal point. And then lastly, we have 808. So again, we go 1, 2, 2 places to the left. So this would be 8.08 times 10 to the second. This is just to confirm that the number of significant figures we accounted for does show up in the scientific notation. So just to make a correction, this should be a 4 here, not a 5. So we talked about significant figures. The next thing that involves significant figures is rounding. So that's what we're going to discuss next, is how do we round numbers, because when we're dealing with measured numbers, maybe we need a certain number, or we need a number to a certain number of significant figures. How do we round numbers? So the rules for rounding are fairly straightforward, and the definition may look intimidating, but we're looking at the digit that's to be removed. So if the digit to be removed is greater than 5, then we just increase the preceding digit by 1. So what do we mean by that? So if we take a look at an example, let's say we have 1,260. And we only want to keep 2 significant figures. So we get the 1 and the 2. So the digit to be removed is a 6. So since 6 is more than 5, we would round the 2 up by 1. So this would become 1,300. So again, since the 6, which is the digit to be removed, is greater than 5, the preceding digit we increase by 1. And it just has to be greater than 5. So what do I mean by that? Let's say we have a 0.067359. Let's say we have a small number. We want to round this to 3 significant figures, 6, 7, 3. So again, what comes after the 3, even though it's a 5, this is not 5 even, it's 5, 9. So 5, 9 is greater than 5 even, so we will still round up the 3 to a 4. So this would be 0.0674. So when we mean greater than 5, whatever comes after the last digit we want to keep, if it's greater than 5, we round up. If it's less than 5, we round down. So for example, if we have 34,380, and we want to round to 2 significant figures. So the digit we want to remove is a 3. 3 is less than 5. So then we would just drop the 3 and the 8 and replace them with trailing zeros. 34,000, or you can write it 3.4 times 10 to the 4th. A very common mistake that students make in this problem is they would just put 34, and that is incorrect. So just imagine if you were working for a company and you're getting paid a salary, say $34,380, and your boss decides, well, I'm only going to pay you in 2 significant figures. So instead of putting 34,000, they put $34. So there's a big difference between 34 and 34,000. So whenever you drop digits, if it's a number greater than 1, those drop digits you replace with trailing zeros. So for example, we'll look at another one. Let's say we have 650,480. So here, let's say we want to keep 2 significant figures. So after the 5 is a 0. Well, 0 is less than 5. So the way we would write this answer is we would drop the 4 and the 8 and replace it with trailing zeros. So this would be 650,000. So that still has 2 significant figures. Now let's say we take the same number and we want to keep 3 significant figures. So we go 1, 2, 3. After the 0, we have a 4. And 4 is less than 5. So we need to drop the 4 and the 8 and replace them with trailing zeros. However, if we were to do that, we would get 650,000. But this wouldn't be correct because we need three significant figures. So how do we write 650,000 with three significant figures? The answer is in scientific notation. So you do 6.50 times 10 to the fifth. So sometimes when you round numbers, the only way to correctly write it is in scientific notation, because there's no way to write 650,000 with three significant figures in normal numerical format. Now the discrepancy comes when the digit to be removed is exactly, again, this is important, exactly 5. So 5000, etc. So if the digit to remove is 5 and the preceding digit is odd, we increase it by 1. If it's even, it remains the same. So we'll look at a few examples of that. So let's say, for example, we have 0.0006750. And we want to round this to two significant figures, the 6 and the 7. So after the 7 is a 5, and this is an even 5, so 50. It's exactly 5. So since 7 is odd, we increase it by 1. So this would be 0.0068. And we'll look at one more. So let's say we have 450, and we want to round this to one significant figure. So after the 4 is exactly 5. So therefore, since it's even, we just drop the 5 and replace it with a trailing 0. So this becomes 400. Now note, it has to be exactly 5. So now if I rewrote this and put this number, 451, and we wanted to round it to one significant figure, well, this is not exactly 5, it's 51, and 51 is greater than 5, so you would round this up to 500. So this rule with the 5 is when it's exactly 5 in the number. Now, when you're doing like a bunch, and this becomes important when we look at doing conversions, when we're doing conversions with multiple steps, we need to make sure that in each of the steps, we keep, quite a few significant figures until we get to the very last step and our final answer. So only at the final answer do we round to the correct number of significant figures. And when you're doing these multi-step calculations, when you're determining the number of significant figures in your answer, it's based off the numbers you start with and which one has the fewest significant figures. And we'll talk more about that last bullet in a second. But here, let's take a look at these examples. So in the first one, we want to round 75,640 to two significant figures. So we go 7, 5. After the 5 is a 6. So since it's greater than 5, we're going to round up. So again, it's going to be 76. And then we replace the 6 and the 4 with trailing 0. So this becomes 76,000. Next, we have 0.00055,349. We want to round this to three significant figures. So note, with a number less than 1, the first significant figure is always going to be the first non-zero number. So after the 3 is a 4. 4 is less than 5, so we just drop the 4 and the 9. So with a number less than 1, if you have to drop digits, you do not replace those with zeros. You just drop them. So this becomes 0.000553. Next we have 950,780. We want to round it to 3 significant figures. 1, 2, 3. After the 0 is a 7. 7 is greater than 5. So we round up to 951,000. Again, since the number is greater than 1, we replace the 7 and the 8 with trailing zeros. When the number is less than 1, any remaining digits that we drop, we just drop them off, drop them out. And then lastly, we have 105,000, and we want to round to 3 significant figures. So we go 1, 2, 3. So after the 0 is exactly 5. And since 0 is even, we just drop the 5. So we have to write 100,000 as 3 significant figures. So we have to write this in scientific notation. And this answer can only be written in scientific notation. Because the only way to write 100,000 with 3 sig figs is to put it in scientific notation. So the last thing we want to talk about is significant figures with calculations. So if we do addition and subtraction, or we do multiplication and division, how do we determine the number of significant figures in our answer? And this is very important because when you're doing measurements in the lab, when you make a measurement, your resulting answer, or if you have to do calculations, say for example, you want to measure the density of a cube, how you measure the side of the cube will dictate how many significant figures are in your final answer. So the volume of the cube is based on the number, the precision of what you measure the side of the cube to be. So addition and subtraction, multiplication and division have 2 slightly different set of rules for them. So with addition and subtraction, the answer should have as many significant decimal places as the number in the operation with the fewest significant decimal places. So what do I mean by a significant decimal place? So to show you an example of what significant decimal place is, if I wrote 10 and I wrote 10.0, 10 would only have a significant decimal place of the tens place. So the 1 would be the only significant decimal place. But if I write 10.0, now the tens place is the lowest significant decimal place. So that's what we're talking about when we're talking about significant decimal places is, is there a decimal point? How many decimal places are significant? So if I just wrote 10 with no decimal point, that would be one significant decimal place, which would be the tens. If I write 10.0, now it becomes the tenths. So for example, if we take 12.5 plus 2.567, well, 12.5 is only known to the tenths. 2.567 is known to the thousandths. So our final answer should be rounded to the tens place, the tenths place. So we get 15.1. Now, for example, if I was to only use 12 plus 2.567, then the answer would only be rounded to the ones place because 12 is the one with the fewest significant decimal places. So I wrote it over here, 12 space plus 2.567. We get 14.567. So if we do 12 plus 2.567, we get 14.567. But notice here that 12 is only has significant decimal places to the ones place. So our answer would have to be rounded to the ones place. So it would be 15. So notice the difference in the two answers. One is 12.5, we get 15.1. When it's 12, we just get 15. Likewise, if we take 12.5678 minus 0.12, we get our answer. Since 0.12 is only known to the hundredths place, our answer should be rounded to the hundredths place. So if you have addition and subtraction, that's the rule you need to follow. Now, if you have a combination of addition and subtraction and multiplication and division, you just use the rule for multiplication and division, which is the answer has as many significant figures as the number in the problem with the fewest significant figures. So whenever we're doing multiplication and division, we're just looking at the significant figures in our original numbers and seeing which one has the fewer or fewest. And that's going to dictate the number of significant figures in your operation. So we take 12.34 times 3.5. The calculator tells us 43.19. So 12.34 has 4 significant figures, 3.5 has 2. So we would round to 2 significant figures. So 43 would be the answer. Now we take 2.3476 divided by 5.67. The calculator spits out this very long number. But since we're doing division, 2.3476 has 5 significant figures, 5.67 has 3. So our answer needs to be rounded to 3 significant figures. So the correct answer would be 0.414. So again, with multiplication and division, we look at the number in the operation with the fewest or fewer significant figures. That's going to dictate the number of significant figures in your answer.